Hi, my name is Filip Leonarski. I am beamline data scientist at the Paul Scherrer Institute, and I would like to give you, in this module, an introduction into the challenge of handling data from X-ray detectors. So, as you know, X-rays can be used at a hospital to look through your bones, but also X-rays can be successfully used to look into very small structures of the living world, so molecules like proteins or DNA. The photo showed here in the middle was the main evidence for scientists to assign a double helix to a DNA molecule. X-rays are still very important to understand how living cells are doing their job. For example, just a few years ago, a Nobel Prize was given for a study of ribosome, and the structure of ribosome used by Nobel Prize winners was obtained with X-ray crystallography. So X-ray crystallography is an experimental technique to find atomic and molecular structure of a crystal via diffracting of an X-ray beam into many directions. What is important is that macromolecular crystallography can be very efficiently done at particular accelerators called synchrotrons. Here, the accelerator works as a source of very bright X-rays, which are multiple orders of magnitude brighter as in conventional X-ray tubes, which you can find when doing X-ray at the hospital or at the airport. Initially, this was parasitic to high-energy physics experiments, but currently synchrotron facilities are built explicitly to provide X-ray light. Synchrotrons provide a continuous X-ray light, while other type of facilities called X-ray free-electron laser produces femtosecond long bright pulses, which allow to study processes occurring at very short timescales. Here at Paul Scherrer Institute, we have both of the facilities. On the right side of the river, you can see a round structure of a synchrotron called Swiss light source, and on the left in the forest, you can see a long tunnel of SwissFEL, Swiss free-electron laser. So for macromolecular crystallography, we do have 3 experimental stations where we can do experiments in parallel at the synchrotron, and 1 experimental station at the Swiss free-electron laser. Beam time at these experimental stations is shared between academic users from all over the world and our industrial customers, which are mostly pharmaceutical companies interested in binding of drugs to potential protein targets. What is a driving force for doing macromolecular crystallography at synchrotron facility are X-ray detectors. Paul Scherrer Institute is a major detector developer. We use so-called hybrid pixel detector technology that was first developed for CERN high-energy physics experiments, but later on it was applied to X-rays. In this technology, every pixel of a detector that can contain millions of pixels, every pixel has its own dedicated readout electronics to find what is the count of photons that hit this particular pixel. The detectors, PSI is doing substantial research on new detector technologies, while there is a PSI spin-off company called Detectris that commercialized two of our previous detector designs called Pilatus and Eiger. And most of currently used detectors at Synchronous facility actually come from Detectris. Currently, we at the PSI are developing and deploying new generation of detectors called Jungfrau. What is specific about Jungfrau is that we really aim to be able to measure with a very high dynamic range. We want to be able to measure just a single photon that hit the detector, or 20 million photons that hit the detector per second. To be able to cover such a high dynamic range, each pixel has actually 3 modes for measurement. It has 3 capacitors to store the charge that was generated by X-rays during exposure. Depending on which capacitor was used, Jungfrau is either very sensitive with a small dynamic range, or is less precise but with very high dynamic range. And what is very important is that these modes can be switched dynamically during the exposure. So each pixel during the exposure decides which of the 3 modes are used. So this has consequence for the output of each pixel. Detector has to provide us information about how much charge was generated in this particular mode, and about which of the 3 modes, called G0, G1, and G2, was actually used during exposure. This allows us to measure precisely both the background, which usually has very low counts, and this black spot in the middle that measures very high counts. Then we need to do some corrections, which is we need to subtract value of the dark current, which is always present for each pixel, and we need to multiply or divide by some conversion constant called gain factor. What is important for Jungfrau is that this pedestal and these gain factors are pixel specific. So each pixel will use a different constant for pedestal and gain. And these constants are also specific for each of the 3 modes, G0, G1, and G2. This results in actually a very high number of constants, because for every pixel, and we can have detectors with millions of pixels, we will need to store 6 constants and load them during conversion. So 3 pedestals for G0, G1, and G2, and 3 gain factors for G0, G1, and G2. Jungfrau is modular. So we produce modules which have roughly 500,000 pixels. So each module can operate at a speed of up to 2,200 frames per second. As each pixel is 16-bit, Jungfrau module can produce more than 2 gigabytes per second. Now, for practical use for macromolecular crystallography, we need larger detectors of size of 4 or 10 megapixels, which will produce 20 and 46 gigabytes per second respectively when operated at the full frame rate. These are very high data rates. And And what we see as a trend, starting from the Pilatus detector that was installed in 2007, up to the Jungfrau that we plan to install next year, that will have 10 million pixels, we see that MX detector data rates double every 2 years. And this poses a challenge to handle this data now and in the future, where this trend continues. So first, we wanted to do data acquisition and conversion of the images traditionally on a mainstream architecture with just a CPU-based implementation. So we had a receiver that is receiving frames streamed over UDP. We had the code for the conversion that I just explained that was optimized to benefit from single instruction multiple data paradigm in the CPU, and there was a routine for compression. Our aim was to process 46 gigabytes per second, while with a very expensive 4-socket CPU system, we could reach 5 gigabytes per second. Looking closer into the results, we saw that the problem was in the bandwidth. So the conversion procedure that I explained before, where for each pixel we need to do one subtraction and one multiplication, could be actually run very fast. There is no limit. The CPU could actually run this procedure around 20 times faster. But the memory and CPU cache could not provide data at this rate. And CPU was waiting for the data. The bottleneck was in moving the data from the memory and cache to the CPU. So we could only handle a 4 million pixel system at 500 frames per second. So we started to look for different solutions. One simple solution would be to parallelize what we have and just install 10 servers. This is inexpensive in development because we have a solution. We just need to scale it to more servers. But this becomes very expensive in terms of hardware, and this becomes non-sustainable in the long run. Because right now we will need 10 servers, but in 2 years from now, we might need 20 or 40 servers. The other way would be to choose a more adapted architecture with which we could actually work with a single server to handle all the data. This would be very expensive in initial development, but cheaper in hardware, and this would be sustainable in the long run. There are multiple solutions on the market currently to help in handling with big data. There are GPUs, there are smart network cards, there are field programmable gate arrays, and there are specialized ASICs. Now, among these four, actually FPGA are a perfect device. First of all, FPGA are cycle accurate with fixed latency and throughput for the procedures. They have very large memory throughput. So HBM2 enables FPGAs to have 460 gigabytes per second per single FPGA chip. FPGAs have Ethernet on board, so they can work directly with the network. And the problem is that development of FPGA is difficult and time-consuming because of the hardware description languages and because of the PCI Express bus that is a low level and requires low-level knowledge of the system. So what one needs to know to develop with FPGAs are just hardware description languages. There is also verification that FPGA is actually doing its job. It's quite difficult. It requires knowledge of simulators, and requires knowledge of low-level interfaces like PCI Express and kernel driver development. And also kernel drivers are very difficult to verify and ensure that they will not crash the system at a very unlikely condition. So these techniques, they have limited productivity. It takes months to do traditional FPGA development projects. The other issue is that most of us who are trained as software developers were not taught about these techniques. These are things that are taught for electrical engineering courses and not computer science courses. So there's also a lot of learning required for software developer to be able to use FPGAs. And I would say that FPGAs have a potential to be used wider if development of FPGAs were easier. And I would like to convince you in the next module that OpenCAPI is significantly helping in making FPGAs more accessible to software developers. Thank you for listening.